All right. Again, I would like to, before the detailed circuit, I would like to categorize the ADC architectures. Yeah, we have many kind of ways to differentiate from this to that. But anyway, for architectures, for example, we have series, parallel, and parallel. What does that mean? For conversion, if you convert all of them, I mean for quantization, if you quantize all the levels with the input, then we call it parallel, all right? And series means what? Step by step, one bit by the other bit, blah, blah, blah. Then we call it series. And in between, series parallel. You can guess that series will be the slowest, but usually you can save some more, you can save more chip area or even power. On the contrary, for parallel, because you compare the input to all the quantization levels, so supposed to be this is the fattest, but nothing is free. Nothing is free. You need to pay for chip area and also power usually. Okay, so how to compromise series and parallel? All right, and maybe this is also the reason why pipeline and successive approximation, actually that is the fattest in series operation. Okay, and this is the reason why we focus very much on pipeline and SAW. Okay, then you'll be really interested. From the very beginning, you learned from microelectronics. It means tens of years ago, humankind had such kind of ADC already. It's easy to understand, but for understanding, it's still very important. So allow me to refresh your mind from your microelectronics. This is V-in, that is the comparator, and we need some kind of DAC. But how to drive the DAC? We need some kind of binary counter, okay? And from the beginning, yeah, you can see, for each conversion, we reset the input, the counter to 0. It means we count, we count the digital output one by one to increase the output of your DAC and compare to your V-in. Until what? Until it sends the reverse signal. Because from the beginning, your V-out is smaller than V-in because it's reset to 0 from the beginning to make sure everything is correct after reset. Okay? And then V-out is smaller than V-in, and you increase the counter and also the output of your DAC, and gradually until your V-out larger than V-in, then the output of the comparator will become 0, right? To stop the clock. The clock for what? To count up the counter. Bingo. That's it. That's very easy to understand. But why I refresh your mind for this? I waste 1 minute for this. Why? Because I would like to show you this. That is, I guess you never learned from your microelectronics. Microelectronics usually always focus on the discussion of operation principle. But to get better understanding, you had get this slide. So this for the green one, that is the analog input. And what is the operation for your DAC, for your ADC? Actually here, I told you already, from very beginning, it is reset to 0 to the minimum. Then you count up, right? 0, 1, 2, 3, all the way your output finally reach the input. Bingo, you got it. Because the comparator output is toggled from 1 to 0. Okay? So at this current moment, we send another very important signal. We call it end of conversion, EOC, to tell your consumers, oh, right now you can read out the counter, or you can latch it as the output, right? That is the correct output according to your V-in. All right? Yeah. So you can see after you send the EOC, you will latch the counter content to be your digital output. That's it. Okay. And how about next conversion? Haha, the same. Yeah, you need to reset it and all the way trace your input. When you made it, you latch your output to the second, to the third, blah, 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 blah. Okay? But what is the problem? The problem is if the input is the maximum, right, for your operation range, then you still need to count up from 0 all the way to the maximum. Oh, guess what? If you have 16 bits, how many cycles you need to wait, the maximum cycle? Gosh, more than 65,000. 65,000多次. Okay? So after you push the button, come on, go. Then you can go, just like me, go back to get coffee after you finish your coffee. Oh, it's still under conversion. It doesn't make any sense. It's too slow. Okay, so what is the major problem? Wow. The major problem is, yeah, from the beginning, after you power on the chip, you have no idea where your output is. So you need to do reset to reset the whole system to be some kind of determined state. Okay? 你要把它恢复到一个你所知道的状态. So you reset everything. Usually we reset to 0. Okay, blah blah blah. So that is some kind of we make the system from unknown to determined. 从未知到已知. Then you can go anything. You can do anything with your system. So for the first time, yeah, you need to make it. But after you spend a long time for your output to catch your input, then you reset it again. It doesn't make any sense because the tracing spend a lot of time for that. And you can see the higher input, the longer time for you to do the conversion. The smaller input, the shorter time. But usually we need to fix the conversion time. Never mind how high or how low your input is, right? So for conversion time or for sampling rate, we always focus on the worst case. That's it. That's really troublesome. Yeah, the conversion rate for such kind of very easy to understand structure actually is impractical. It never be practical because it's too slow. So what we can do is, after we tracing, from the beginning reset to 0 and all the way to trace the input, when we made it, don't reset it. That's too stupid. We simply fool around. The output fool around the input. How to fool around? Okay, allow me to show you this. Aha, we call it tracking ADC. Again, the initial is the same. You need to wait until the output reach the input. And then, very easy to make your output fool around your input. 让你的输出在你的输入旁边鬼混. How to make it? If your output is smaller than input, then you need to increase the counter. But after some cycles, you are above the input, then you decrease it. Okay? Up and down, up and down. That is a very easy to understand way to make your V out very close to your input. Never reset it. If you reset it, you are stupid. Don't waste your time. Don't waste your precious time to do tracking. It doesn't make any sense. So tracking is only for the initial. Okay? After power on, you need to track your output. Your output needs to track your input and then fool around. 鬼混. Yeah, with your input. That's it. Okay? Wow. In this way, I promise you, you can enhance your conversion speed by thousands, even tens of thousands times. Okay? But what is the problem? The problem is here. If your input is fixed, you have DC input. Yeah, ADC needs to operate until DC, right? I mean for your input signal. It can be to your DC or to Fs by 2. That's it. Okay? So when you apply some DC input, what will be the problem? We call it bit bubble here. The DC is fixed. So consumers always expect the output will also fix because I apply DC signal. You need to get DC output, right? But sorry for that because your output will full or not. Your input, count up and count down, count up. Oh, so count up means the output will be increased, then be decreased. Even though it is only full or not your input, but you will get different output. Especially because you can say, hey, there is no much indifference, right? So what does it mean? Oh, you have 1 0 1 1 0 0 0 0, for example, then 0 1, maybe 1 0, then count down 0 1 0 0. Okay, but for the MSB, they should be exactly the same. So only the LSBs, maybe 1 or 2 bits, they will get a lot of 1 and 0. Yeah, and some kind of variation. We call it bit bubble. Okay, that's it. Are you happy with the condition here? Usually not, because you really know that your input is a DC. Then why you get some kind of AC output, even though only the LSB bits are changing, right? Anybody? To solve the problem here. Okay, my hint is how to make your output exactly the same for DC input. How to solve the problem? The major problem is here. Okay? How to solve it? Okay, please go back here. Oh, here. The hint is from the very beginning. See? The latch. When you say okay to latch the output, to latch the counter to be your output. See? So never mind you focus on falling edge or rising edge. But not the both, please, not both. Only one. You can choose rising edge or falling edge to latch the output. Bingo. This problem will be solved very, very easily. Okay? Again, this is some kind of innovation. 2 innovations here. Yeah? From the original structure, well, it is so easy, but it's quite painful to have such kind of very long conversion time. Okay? So we modify the first to the second. But you can see, what's the difference? Not much. You have DAC, you have counter, you have comparator. Wow, exactly the same, right? So what is the major difference? Huh? Anybody? What is the major difference between those 2 structures? Here. See? You need to count up and down. So you need up-down counter. But for the first version, you only need up counter. That's it. All right? And how to control the up and down counting? Oh, simple to test again. Here. Right now, the output is not for end of conversion. No. Yeah. If it is high, it means I am smaller than you, so I need to increase myself. You need to count up your output. Okay? And then if it is 0, I'm too much. I'm over you, then I need to count down. So the signal for your comparator output right now is not for EOC. Actually, is to control the count up or count down of your counter, and also if you would like to control your latch. Okay? So the first innovation is we have almost exactly the same structure. Yeah, you have comparator, DAC, latch, memory counter, blah, blah, blah. Okay? So the second IP is supposed to be violate the first. Okay? Yeah, you need to pay royalty to the first because you have everything it has. So, but by only modify the up counter to be up down counter, you can make such kind of excellent achievement to speed up the conversion by thousands or even tens of thousands times. Okay? So anyway, yeah, you need to pay royalty to the first, but very little. If they are not happy, shoot you to the court, you still pay very little. Okay, we have some kind of IP court, 制裁法院. Not somebody kill anybody. No. Not for that kind of court. Yeah, for IP we have special court. You sue the other companies for this or for that. Then usually the second IP will get the most benefit. I mentioned already from the very beginning. And the second innovation is this. To solve the problem here, you only need to latch your counter, okay, at origin or falling edge, but not most. Anyway. And then we can go further. All those seems much in digital domain. Let's go back totally in analog domain. Okay, here we call it single slope integration. You can see before conversion you reset it to 0, right? And then open the switch. You can start the conversion. Then the current will be used to charge the capacitor. And from the beginning I'm smaller than you, right? But after charging, after some time, the output here will be larger than V in. Then again, you send EOC, okay, and latch it, blah blah blah. So the operation actually is much similar to this one, okay, but you don't need DAC. Oh, congratulations, because again, if you would like to achieve 16-bit, then the DAC is really hard to design. Really hard to design. Okay, but right now you don't need the so-called DAC. Current source and capacitor can help you to solve the problem, to save the most cost for the original structure. But the operation principle, to be honest, exactly the same. Okay, so allow me to show you. Anyway. See? Almost the same. Maybe the only small difference is here. For the previous one, you have DAC. You count it up. So the increase of your output look like this. Right? But right now, it is very smooth, continuously. That's it. And this is the reason why we don't need DAC. Right? Okay. But what is the problem? With this, I promise you, your cost, the chip area, will be much lower than before. Again, nothing is free. What is the penalty? What is the disadvantages? If we go back here, you will see, your output right now depends on not only clock. For our previous one, it depends on clock, right? But right now, not only depends on clock, but also the current, the capacitor. Okay, and also VOS. For the previous one, the same. Okay, we have the same problem, but we have the same problem, but right now we get more. The accuracy for your current, for your capacitor will also have some kind of impact on your output. And according to process variation, how much you need to expect for your INC? Usually 30%. Okay, peak to peak. Wow. If you are unlucky, one chip get the maximum current, the smallest capacitor, and the other one get the smallest current, the larger capacitance. The overall deviation will become 60. Okay? Wow! It's really embarrassing. It means what? With the same input, your output deviation will be more than 60. It is possible. Okay? So how to control the absolute accuracy between your between your current source and your capacitor? Wow, it is a big question. Okay, so nothing is free with such kind of very easy to understand, very small, very cheap architecture. Actually, the performance is really no good. Okay, because it deviates too much. So we are intelligent humankind. We try to solve the problem step by step. So the next step is for dual slope instead of single slope. For dual slope, you can see we have two steps. For the first step, we charge the capacitor with different slope. Okay, it means the charging, the phase 1 and phase 2. For phase 1, the time for charging is fixed, but the current is not. The current depends on your input. Okay, and for the next phase, on the contrary, what is fixed? The current is fixed. Okay, but the time is not. And you can see that the higher input, okay, the higher input, the more current, but the time for charging is fixed. Okay, so proportionally, you will get higher voltage according to higher input. I mean, you will get higher voltage on capacitor according to higher input voltage. They are dependent. They are proportional to each other in theory. Okay, so how about the next stage? I told you already, the discharge current needs to be fixed. But how? Okay, you change your the switch from input to V reference. So I don't care what kind of input you have because it is connected to reference voltage. Reference voltage is fixed. And this is the reason why the current flowing through R1 is fixed to charge the current, the capacitor. So the slope is fixed. But the higher input, the higher capacitor voltage. It means what? The longer discharge time. Bingo. So by counting, you still get larger output. So the digital output will be proportional to your analog input, right? That's it. But even though the structure is a little bit more complicated than this, but you can see, according to your output equation, that is simple mathematics. Do it by yourself. Yeah, within, I cannot say seconds, but minutes, you can get it. 只要几分钟，你就可以推出这个答案。Wow, wow, what? You can see R and C are not here. Because for charging and discharging, you use the same R, the same C, right? So they cancel each other for charging and discharging. So finally, you only get this. Congratulations. Okay? Nothing. No R, no C. It means R according to I, right? So no I, no C terms in your final output. Congratulations. Congratulations. Okay? Yeah. You reduce the variation very, very much. But you need to pay for it. Pay for what? The circuit and the operation principle is a little bit more complicated. That is the usual case. All right? All right? But right now, what problem you need to face? Again, clock. Because the higher clock, you will get, even with the same V in, okay, the higher clock, you will get more output. All right? So you need to control the accuracy for your clock. Usually, it is not a problem because we can apply crystal. Okay? With crystal clock generation, I think good enough. Okay, so we can forget about the accuracy of the clock. But anyway, if you would like to apply some kind of on-chip crystallized, especially crystallized clock for money saving, right now, according to Holtec, to my memory, for their last two visits, they told me, yeah, for such kind of crystallized on-chip oscillator, the accuracy maybe 1% after calibration. According to process variation, the output frequency, the deviation of output frequency is still tens of percent. Okay, but after calibration, yeah, they can, to my memory, they can make it, yeah, around 1%. Okay, and the ppm maybe tens of ppm according to temperature variation. I think that is good enough for daily life applications. Okay, but not for communication. For communication, the spec is much smaller than this. How about 0.1? No, much smaller than that. Okay, yeah, for telecom, because the operation speed for our wireless communication right now is too high to be true. So they have very tight control about this. Anyway, the boss of whole tech still hope 1% is no good. They would like to push for 0.1%. Okay, without crystal. Yeah. As the engineers in the company, yeah, you need to fit the wish of your bosses, otherwise you will be fired. Anyway, they try very hard to make it from 1% to not, maybe not 0.1%, maybe 0.5 first, and then for the next step. Okay. Anyway, two major issues, clock, but it can be solved with crystal. So we still need to face, yeah, the offset voltage of the op-amp of all the comparators still has some kind of impact for your output, especially for high accuracy ADC. Okay, so how to solve the problem for V offset? Wow, allow me to show you this. Quad slope. Quad means four. Quadruple. Okay, full slope. So you can, from single slope to slope to dual slope, right? We solve the inaccuracy problem for R and C. But how about the offset? We need quad slope. You need to double the operation. We have 4 phases. Okay? Why we have 4 phases? You can see here. Phase 1, charging. Phase 2, discharging. Charging, discharging. So totally 4 phases. All right? But the concept is, for the first 2, even for the first 3, the time for charging or discharging is fixed. Okay? So in theory, first phase, 50, T, 50% of T, T by 2. Okay? Yeah. Half T, and 1 T. So totally 2 T here. But for what? Okay, very brief explanation here, VOS. Never mind it is positive or negative. If here is positive, it means what? Never mind you charge or discharge according to superposition principle. Okay? The charging current or discharging current has input for charging V in, for discharging V reference. Okay, very similar to dual slope one. But the second impact from VOS. So for VOS, if it is positive here, I don't care you are discharging or charging. I don't care, because I am positive. According to superposition principle, it will always charge with your capacitor. On the contrary, if it is negative, okay, I don't care you are charging or discharging, you get the same impact discharging. Okay? Okay? Charging or discharging means what? It will cause extra error. If it is positive or negative, yeah. For example, if it is discharging, so what is the impact? If the VOS impact on C is discharging, it means what? It is charging. Okay, yeah. To fit the explanation here. Okay, so if it is positive to charge your capacitor, so you can see during the first charging, the first phase for charging, because it is also help you to charge. So you will get higher output on your capacitor, I mean in magnitude. Okay? And also that during discharging, it still help you to charge it. What's the consequence? Ideally, you need to reach here, right? But in practice, it is pushed later. You get extra time for P1 and P2. Okay? On the contrary, if it is discharging, I promise you, you will get delta T negative. Why? Because during charging, it has some kind of reverse mechanism to reduce, because I am discharging, you are charging. So the magnitude of your final output will be here, less than the ideal one. And how about the discharging? Because I help you to do discharge, so it will discharge to 0 earlier than the ideal value, right? Right? So never mind, it is positive or negative. For charging or discharging, they have the same impact. Okay? So how to deal with this one? For example, the total charging discharging time is T, right? Right? So for the phase 3, it is ideally T, but we subtract delta T. Because I told you already, never mind it is charging or discharging, you get the same impact for your VOS. So for the next charging or discharging, you still face the same thing. Okay? You still face the same thing. So for the same T here, the same T there, I simply steer away delta T from the phase 3. Okay? So the impact of 1 T is cancelled here. And finally, we can get perfect result. Okay, that is what we hope. Okay? That's it? That's it. Yeah. To derive is really hard, but by explanation, I hope you can get the most important idea about the operation principle, how to cancel the VOS. Okay? Anyway, it is reported that we can achieve 16 to 17 bits in accuracy, but you need to control the linearity of your resistor and capacitor. Okay? For on-chip resistor, on-chip capacitor, is no good, because we have VC1 and maybe VC2. VC1 maybe is not so harmful, but for VC2 is really harmful, because what is VC2? Voltage coefficient. This is for first order, for second order. First order, according to linearity, I think it's not harmful. But second order means you will have some kind of curvature, right? It will harm the charging and discharging. It will never be a linear one. It will be some kind of curvature of So to achieve 16 or even 17 bits in accuracy, the resistor and capacitor needs to be highly linear. What does it mean? You had better make VC2 to be 0 or very, very close to 0. So on chip, you need to select carefully. You have many kind of resistor, but maybe only one kind of capacitor. Anyway, okay, you need to be very careful. Unless the VC2 of R can be compensated for VC2 of C. The curvature of both can cancel each other, but it's really hard. Okay, so you have to better choose the linear ones. Okay, that is what my recommendation for you. How humankind achieve such kind of very high accuracy? Simply because all those are off chip instead of on chip. For off chip, you can buy very expensive, very luxury resistors, capacitors to make it. But for on chip, forget about it. On chip, what kind of accuracy you can achieve? Again, my recommendation is still 12. Okay, no better than that. I mean for ENAB. Okay, and also that for quad slope operation, you can see the circuit, the operation becomes very complicated. And you need charging, discharging, charging, discharging, so the conversion rate will also be reduced. Again, nothing is free. To enhance the accuracy, you need to slow down your operation. Okay? Yeah. That is some kind of ugly truth. Anyway, that is only for fun. Why? Because usually we don't apply such kind of very old architecture because they are too slow. Okay? So, for current design, I told you already, two major mainstreams. 这两种主流 SAR or pipeline. Allow me to show you SAR operation first. Again, it is not hard to understand. All right? Allow me to show you why it is not hard to understand. Because our ancestors did the same thing in the past. I cannot say thousands of years ago, but at least hundreds of years ago. Okay? When our ancestors, I mean old humankind, would like to weight something, this is a scale. To weight something, we just use a hook, yeah, to pull up the goods. They would like to wait, okay? But first of all, they will use the largest one. Yeah, put down the largest one to the other end. Okay, so if you look like this, oh, not enough, then the second largest. Oh, too much, they take it away, the third largest. Got it? Got it? I don't think our ancestors will always use the smallest one. Oh, one, oh, not enough, 2, 3, 4. Okay, that is single slope, one by one. Stupid. Yeah, humankind, we're not so stupid. We are intelligent. So from the biggest first, not enough, the second, too much, remove it, then the third largest. Got it? That is the idea for SAR. Okay? So again, our ancestors applied such kind of successive approximation concept at least hundreds of years ago. As a modern humankind, you are the better fully understand the operation principle for SAR, because it is really good for your future ADC design. And this is my first recommendation. If you would like to do any kind of ADC, this is the first step, the first design for you. Easy to understand, and you can achieve something than nothing, okay? Because it is, in theory, not so hard. So, in theory, we call it binary search. In the middle, up or down, okay? Not enough to the top, too much to the bottom. Okay. Anyway, allow me to show you this. The concept here, for example, your input is here. Okay. So from the beginning, as our ancestors, as our ancestors, the largest first. So according to our circuit, what is the largest? Because we have deck, right? So it means MSB first. MSB means what? 50% of your reference, of your full range. So from the beginning, the input here, so I put the largest MSB. Oh, 50%, not enough. Then go for next bit, another 25%, right? Here. So from 50 to 75. Oh, it's still not enough. Then, for the third bit, we get 1/8, right? Oh, too much. Again, sorry. Like our ancestors, I told you, too much means what? You need to remove it. And then get the next bit. That's it. That's it. Very easy to understand. Too much is so reset it instead of keep it. Okay, from the beginning, again. Yeah, I would like to help you more. From the beginning, MSB 1/2. Okay, 50% first. Not enough. Keep it. We need to keep MSB there because it's not enough, right? So after comparison, after each bit operation, we need to decide whether or not to keep the current bit or to remove it. I mean reset it. Okay, so it's not enough for the next. Oh, it's still not enough, so keep it, right? Keep it. And then the third bit, too much. We need to remove it. So we need to reset the third bit. Then go for the first bit. Okay? Because for each time, a new bit will cover 50%. It becomes smaller and smaller and smaller. And you can see the difference between your output and input will also, the error will be reduced by 50%. Right? Right? So that is the beautiful operation principle for successive approximation. Got it? The more bits, in theory, you will get, the better accuracy. And how about the conversion time? Sorry for that. N bits means what? You need to compare n times. So the throughput is 1/n. Okay? After n cycles of operation, you will get one result. That is for throughput. Okay? And then, if you would like to speed up the operation, what you can do? Very similar to cyclic deck, right? We use the same circuit to convert first bit, second bit, blah, 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 all the way, right? So I told you, for such kind of cyclic operation, if you expand it to be linear, it will become pipeline. So the same. If you would like to speed up it, I hope we don't have such kind of throughput 1/n, right? So we have n stages. Yeah, they do similar operation. They do similar operation like this. But from the beginning, for example, n bit, right? So we have Tn-1 for the first stage. After comparison, okay, then pass to the second stage to compare n-2 all the way to D0. That's it. That is the concept for pipeline. That's it. Okay? Very similar. The concept, so you can see, humankind apply the same idea again, and again, but into different fields. Okay? In DAC, we apply such kind of from cyclic operation to pipeline. So we make cyclic deck into pipeline deck. And here the same. For successive ADC, successive approximation ADC, we use the same structure, the same hardware to do it from MSP to LSP cyclically, right? So nothing is free. To speed it up, we can make it from cyclic operation to linear operation, pipeline operation. But the hardware will be increased by n times. That's it. Okay. So till now, I hope you fully understand not only the operation for SAW, but also for pipeline, because you simply change the cyclic operation to linear stage, one by one, one bit by the other bit. That is so-called pipeline. That's it. Okay. And it means what? The design for pipeline ADC and the design for successive approximation ADC are quite similar to each other. Okay, the only difference is one for all, that is successive, but n for n bit, that is for pipeline. That's it. Okay. Yeah, this is the data flow for binary search. Why I show you this? Because, okay. We are analog IC designers, but for the control circuit, you can see the output is only 0 or 1. Enough or not enough. So the input for control circuit actually is binary. Okay? And then you need to control the ADC. How to turn it on or off? How to turn on or off? Still, the control bit, I mean for your output, is also 1 or 0. So it means what? Control circuit is fully in digital instead of analog. So to make your life easier, I hope my student or even you, my student in the lab or the student in the class, I hope that you can apply cell-based design for the digital one. Because with cell-based design, usually what you see will be what you get after fabrication. No error. Okay? So you only need to focus on the analog part. Anyway, it will make your life much easier than before. That's it. Yeah, hopefully you don't need to spend a lot of time to design such kind of digital part. It's time wasting. But you will argue, hey, how can I do with this? Okay, here. Yeah. This block diagram is for you to do coding according to your Verilog or something, VHDL. Right? You just write, from the beginning you need to set or reset something, then under what kind of situation, blah, blah, blah. All those will be much easier for you to do coding in Verilog, VHDL. Okay? Maybe you will complain, hey, I'm only good at full custom design. I have no idea how to design in cell-based design flow. No worries. You can Google online. Okay, Google is really fantastic. Yeah, you simply input star and Verilog, or maybe even code, or VHDL code. I promise you, somebody will always do something on the web. So you just Google it and download the code. Then you can do all those. You don't need to do coding by yourself. No, you simply copy and paste. You can make it. Okay? So the major issue for you to learn the process for cell-based design, that's it. Okay? It is ridiculous. Sometimes you don't even need to do the coding for Verilog now. What is life? Your life will become much easier than before, right? Okay, but if you would like to do it by your own hands, allow me to show you such kind of non-redundant star circuit. Okay, it is published maybe more than 10 years ago. Anyway, that is from my own lab. Okay, Professor Chen Liu's lab, Liu Shen教授. Okay, the best analog IC design lab. Yeah, in Taiwan. I mean on campus. Okay, and this circuit was created by my juniors and published on JSSC to my memory. Okay, wow. Please pay attention to this. Non-redundant means what? The smallest. Okay, in circuit size. The simplest. You don't waste any circuit for redundancy. 完全没有重复，没有冗杂多余的东西，我们称作冗余 redundant. Okay, nothing redundant. It means it is the simplest. It is the cheapest. Okay, but how to prove it? I have no idea. But that is my junior claim in their paper. Redundant, blah blah, and also accepted and published. Now, believe it or not, I have no idea. Okay, and that is the detail for each stage. Blah blah blah. Not so complicated. Never mind, you know it or not. You simply copy and paste, because for our first start, not in ADC, no, in TDC. Yeah, we apply such kind of concept from voltage domain to digital to time domain. We were the first on Earth, so we published our paper again on JSSC. Okay, the top one IC design journal. Oh, the reviewers thought, wow, it's quite innovative because in TDC, nobody do any kind of SAR operation. We were the first. But in theory, the same, right? You only change. You change what? This is not voltage. This should be time. That's it. Okay. But in time domain, usually we don't plot the waveform like this. Usually, time needs to be horizontal. Okay, so my student just rotated 90 degrees to please the reviewers. But in theory, you simply delete it and then okay. So it means what? That is the input time. Okay. So for the first comparison, 50% of the reference time. So you have input time and reference time instead of input voltage and reference voltage. Oh, piece of cake, right? So the idea is still the same. The input time is here. So for MSB, not enough. Second MSB, not enough. Third MSB, too much. Reset it. Blah blah blah. The same, right? So we don't create it. We didn't create the idea by ourselves. No, we simply duplicated the idea from voltage domain to time domain and realized it. But the major difficulty is not the idea. Okay, is how can we design reference time? Oh, that is another story. Okay, but anyway, the most innovation is to copy and paste the idea from this domain to the other domain. Okay, and the most challenge is to design such kind of reference time. Okay, that's it. That's it. We made it. Then publish in the top 1 IC design journal. You can do the same thing in the future if you are paper lovers. And then allow me to show you the most innovative structure I had ever read for SAR ADC. This is the best of the best. Okay? You can see from the title, SAR ADC with capacitor array. What does it mean? Piece of cake. Everybody does the same thing. But please pay attention to this. The authors claim that they eliminate DAC. If you look back, the original structure, you need, DAC. For SAR operation, for SAR ADC, you need DAC. But somebody, not only one. Yeah, some humankind, some authors claim, in our SAR ADC, we don't need DAC. Is it true? Let's wait and see. Okay. Again, I hope I'm the teacher to provide you the most help. Anyway, I have no time to go in any kind of detail. How to design a good enough op-amp or comparator, right? How to design the switches. That is your own business. Okay. You can also Google online or search through IEEE Explorer. You can get a detailed circuit, but unluckily enough, usually nobody will show you the W, the L, the bias. You need to try it by yourself. That's it. Okay? Don't ask me how much width, how much length, how much bias. The dirty jobs needs to finish by students or by engineers, not by their bosses. Okay? The major role for your bosses, I mean professors or your managers, project leaders in the future, if they are good, they need to explain everything. I mean in concept, as clearly enough to help you get full understanding. That's it, not for detail. Okay, maybe in the company, somebody already designed something related to your new one. Then you can get the detailed circuit and modify. You're lucky. Okay, that is the usual case in IC design houses. You don't need to do anything from the very beginning. Not like on campus. Always you need to do it by yourself from the beginning. But in IC design houses, they have many kind of excellent, successful design for you to refer and to modify. Okay, so you don't need to worry too much about the width, the length, the bias. You just modify it from the previous successful design. Okay, that's it. So in IC design houses, the most important issue is to get full understanding first. Okay, and hopefully I can help you the most. Why deck eliminated? If you look at this, hey, look, there capacitor array, yes, but where is deck? No, right? There is no deck in theory. Okay, but later I will explain. The deck is embedded into such kind of structure. Yeah. So I explained the operation first. Anyway, this is the most innovative paper I had ever read for SAW ADC design. Okay? Yeah, how to understand the operation principle of such kind of innovative structure? Let's go from the very beginning. From the beginning, you still need to, for every conversion, you need to reset. Okay, reset means what? You need to connect all of them to 0 and this one also to 0. Yeah, nothing on the capacitor. So in theory, 0 voltage on all the capacitors. Okay, then next step. Input sampling is not the first step. The first step is still to reset. Okay? And then next step, input sampling. Input sampling means what? We switch all the capacitors to V in. Okay? Got it? And then next, holding. But before folding, how to sample it? You need to close the switch. This node to ground and all the other nodes to V in to make all the voltages on capacitors be exactly the same as V in. And then holding. How to hold V in? Okay, look, open it. It is open already, right? After you open the switch, then you turn all the switches from the right to the left to ground. During such kind of switching, you don't have any path to discharge the capacitor because open, and look into the comparator. It is, in theory, it has infinite resistance. It's still opened. Open means what? Infinite resistance, right? So open here, open there. Oh, no way to charge or discharge all your capacitors, right? Right? What does it mean? No way to charge to discharge or charge the capacitor. It means the terminal voltage for the capacitor should be exactly the same. Should be exactly the same after switching. Okay? But what is the voltage you sampled? Here, I told you. For each capacitor, the difference is V in, right? Because this is 0, that is V in, right? And after switching for holding, you still keep the same thing, V in, right? But right now, this node are all 0. What does it mean? The other node needs to be minus V in. Oh, really smart. Really, really smart. Okay? And then, one bit by star operation, bit by bit. Again, MSB first. That is the always case instead of usual case. For star operation, MSB first. Okay? So, MSB switch from 0 to 1. 1 what? Please pay attention to here. Right now, to reference instead of V in. Okay? According to superposition principle, if you forget about V in, if everything is clear from the beginning, 0 voltage, I mean. Okay? So what is the impact if you switch from 0 to 1? I mean connect to V reference. Oh, simple to death. 簡單嚟講咩事？ Why? You have 8C here. And how about the others? 4 plus 2 plus 1 plus 1. They are also 8, right? So what will be the consequence after the switching from 0 to 1? 1 to V reference. You have AC, I have another AC. So in the middle, you get V reference by 2. Got it? But according to superposition principle, the impact of V in and the impact of such kind of switching for MSB, according to V reference, you need to sum them up according to superposition principle. 重叠原理让你把 V in 的冲击跟你把巴西切过的冲击直接加上去就对了。You learn it, I mean, in second year of your bachelor degree. Okay? I don't need to persuade you to believe it. No, you need to believe it a few years ago. If not, I don't think you can show up here. Right now, you are graduate students instead of bachelor students. You learn everything from your fundamental circuit theory instead of microelectronics, okay? For such kind of superposition principle. Anyhow, that is really innovative because for MSV you can see reference positive, V in minus. Okay, so what does it mean? V in is here. I try to subtract V out from V in. Okay? I mean, I would like to subtract the impact of reference from V in. So for MSV, 50%. I subtract you. Okay? If I am lower than you, after subtraction, you will get minus something. Minus 2. So you need to pay much attention to the terminal. We attach this node to inverting input instead of non-inverting input. You need to be very careful. So input here, and I minus you. V reference minus you. If I am smaller than you, after subtraction, we will get minus result here. But it is connected to inverting terminal, so you will get 1. Because here for positive and this 0, I'm less than 0, so you get 1, right? That's it. And 1 means what? Not enough. We have 2 decisions. Not enough, keep it. Too much, reset the current bit, right? That is what I told you for SAR operation. So anyway, just take this for a very good example. For example, your V in is here. So after MSV is switched to V reference, is here. That is the reference output minus the input. It is negative. You get 1 for the comparator output. Congratulations, you need to preserve it. Okay, don't reset it. So let's go for next bit. 50% and the other, and 1/2 and then 1/4. Too much. It means the reference voltage is higher than V in. So after subtraction, it will become positive here, right? You are positive, but this is, you are higher than the non-inverting terminal, so you get 0. 0 means what? Reset too much. So reset current bit, not all those bits, no, only reset the current bit. So this switch needs to be reset back, just like that. And then we apply the next bit, the third bit. Okay? Not enough, so we get 1. Keep it. Go to the next. Okay? Too much. Finally, because too much, right? So you need to reset the last bit. So you get the other one. Okay? So what is the final result? According to the operation explanation here, we get 1, 0, 1, 0. That's it. Where is the deck? It seems the circuit doesn't has any kind of deck. But I told you already, such kind of minorly weighted capacitor array for DAC right? You say, wow, they look much similar to each other, right? Okay, allow me to help you more. Actually, this analog part is used for all those three. Okay? It replaces all, 3 in 1. How can I say replace? The function is 3 in 1. Sample and hold, right? On the capacitor array. Deck, also on the capacitor array, right? And then comparator here. See? 3 in 1. That is the most innovation. So, even though the authors claim that they eliminate deck, that is only, I can only say that they explicitly eliminate deck. Okay? But implicitly, in hand, they embed the deck into the structure, because I told you already, this is the something 3 in 1. This is 3 in 1 structure here. Congratulations. For all the others, they are digital. This is analog. All analog part here, so you only need to apply cell-based design for your digital circuit. Please, for your future design, this is the best for you to start your new design. Okay, reference to this. But you still need to pay attention to, how to, for accuracy, you need to design good enough comparator with as small VOS as possible. And then how to match 1 to 1 to 2 to 2 to 4 to 8. You need to be very careful, either by good layout pattern, but it will become too complicated, or by calibration. Okay, that's it. Okay, maybe, especially for MSB, maybe you need to fine-tune some of them. Not all of them, too complicated. Okay? Anyway, anyhow, that is a very good structure. So allow me to finish everything for such kind of style design. Yeah, you have some kind of 1C, 2C, blah, 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 and how to do the layout. This is not so bad recommendation. But again, the slide is from Professor Huang Yi教授. Okay, right now in Taipei, National Taipei University in Sanxia. Anyway, there are 2 major errors from his students. First of all, the mistake in schematic, there is another 1C for dummy. Okay, and the dummy here still needs to be switched. You can see? It needs to be switched. In the past, dummy capacitor doesn't need to be switched, right? But in this circuit, it needs to be switched. Yeah, 2 C's. And the even more serious mistake is here. For MSB layout, the concept is quite good for you to learn. All right. For MSB, you can see we split MSB capacitors into 2 halves. To the left, 50%. To the right, 50%. And also, the larger one had better to the boundary. Okay, so you can see MSB 50% to the rightmost, 50% to the leftmost. And then the second bit, 32C, 50% here, 50% there, all the way to the middle. And then how about LSBs? It's not good. It's not good. You can do something better. The most serious mistake is here. Professor Hong's students would like to split 1C into 2. It violates the most important layout rule. You can only apply unit cell layout for all. Okay? But unit cell is 1C, 1C. So correct. For 64C, actually, it is realized by 64 1Cs. Correct. But here is incorrect. You will get too much variation after fabrication for 50% of C. No. It's really bad. Okay, so what is my recommendation? Okay, allow me to show you something. Yeah, for 1C, because we have two 1C, right? So you can, in the middle, we can have 1 and 1. This is in the middle. Okay, and how about 2C? We have 2, right? 2. And how about 4C? We have 4. Bingo! They will still have common centroid, except for 2 1C. But 1C and the 1C, they are the least, right? So we don't care. All right? Face the consequence, because that is the least important one. But for the others, 2C here, the centroid here. 4C and 4C is here. And AC, the same thing. You say, hey, how to apply AC? Okay, 8, 8, 8. 8, 8, 8. Okay, stay in the middle. And for the rest, you need to have dummy. That is another very important issue for you. Okay? So the third problem is you cannot have such kind of empty space. No. For all the empty space, you need to apply dummy capacitors. Okay? Got it? Otherwise, you will have overetching. Too much overetching according to the space. Okay, the empty space. No. So allow me to do rewording for you. Yeah, 1C, 2C, 2C. Sorry. And 4C, right? 8. So 1, 2, 3, 4, 5, 6, 8, 6, 7, 8. And then dummy. Okay, dummy all the way. Got it? Not only this, but also dummy. I mean D all the way to surrounded. Okay? Got it? Even at the corners. It can ensure you not so bad accuracy after fabrication. Otherwise, your angle will be really bad for such kind of capacitor layout. Okay, but nothing is free. To make it like this, the routing sometimes will become too complicated. If you have 12 bits or even higher bits for that, okay? So you can compromise what? Don't compromise MSB, because MSB are much more important. You can only sacrifice your layout for LSB. Okay, I mean, if it is impossible to do something this, it's okay for LSB, but it's not okay for MSB. Okay, got it? Not only the capacitor layout, but also the switches. Again, the larger capacitor means what? The larger switches. Okay, proportionally. So how to create larger switches? Again, unit switches connected in parallel. All right. So you may say, for easy routing, 1C is incorrect because we have two 1C. Okay. But anyway, 2C, 4C, 8C, easy to understand. But they don't have common centroid layout for the switches. Actually, switches are not so important. So it is okay. But if you would like to make them even better, then you can try this. But the routing will become much more complicated. Okay, for example, 1C here, 2 and 4 and 8. And how about 16 here? How about 72? There. Here, there. That's it. Do it by yourself. Okay, but I don't recommend you to go this. Why? Simply because it's too complicated. And all those switches, they are not as important as capacitors. So my recommendation is focus on capacitor layout. And if it is too complicated, then sacrifice your LSBs. Not so complicated, okay? But again, you need to fill all the empty space with dummies. That is a very strong requirement for you, okay? Yeah, and after that, just get the chip fabricated and then face the consequence, okay? Yeah, for capacitor array, this is for your reference. On chip, if you do do not so bad layout for them, then the matching accuracy can be as 0.10, so 0.1%. So what does it mean? 10-bit inaccuracy. With capacitor array, without any calibration or a very complicated layout pattern, to make your ENAP better than 10 is also some mission impossible. Okay, that's it. Yeah, and then, okay, we can hybrid your flash and SAR capacitor. There's some resistor string and the capacitor hybrid, both of them. So the idea is for MSB, for example, you also apply SAR to check the closest, because you can guess. After if you compare all of them one by one, you will get 1, 1, 1, 1, 0, 0, 0, 0, 0. So we want to find the boundary between ones and zeros. Okay? But how to find the boundaries? By SAR. Okay? You compare your V in to the middle. Not enough. Then to the top. Too much to the bottom. Okay? Then with SAR operation, we can find the closest two quantization levels around V in. Okay? 1, 2, and V in between. I don't care where is V in, but this is 1, that is 0. Okay? Through SAR, you can find those two. Then connect it to the capacitor array. We explained already. So you can switch all the way to find LSBs. Bingo, that's it. Okay? Yeah. This is a very good idea. Yeah, that is. And on the contrary, you can reverse it. MSB by capacitor array and LSB by R string. Okay, as you like. We are from democratic countries. We can do everything. Yeah. Unless prohibited by our law. Otherwise, you can do everything. Okay? So if you would like to make it better, you need to do calibration. Calibration usually through, here, R string instead of capacitor string, because to turn on and off resistors will be much easier and less noisy than capacitor. No. Less impact from noise and interference with R string. Why? I told you already, if you would like to do something like this, no DC paste to leak the error, the noise accumulated here or there. Okay, so usually we hate this. And this is the reason why for calibration, usually we have R string. Okay? Yeah, because R string is more immune to noise and interference. I mean, compared to capacitor string, it doesn't make any sense. Okay? Anyway, anyhow, that is for calibration. Okay. Next time, I will go for the fattest structure for flash. But what you see here is totally different from most flash ATC you learn. Not maybe different from your microelectronics and from the other analog design, analog IC design textbook. Why? Because they don't have, usually don't have preamplifier. But for real design, you need. Why? Next time I will explain. Hopefully next week I can finish ATC because it's already the beginning of June. We have only few classes left, right? So hopefully I can teach you, I can fully cover PLL, then a little bit time for DLL. Okay, because PLL, DLL, they are the second important IP for analog design. Okay, thank you all.